Assalamu alaikum. I am Aisha Nadeem, an MS chemistry student, and today I will be presenting on molybdenum disulfide and hexagonal boron nitride and their importance in modern materials chemistry. First of all, we will discuss the introduction to molybdenum disulfide and hexagonal boron nitride, then their chemical bonding and electronic structures, and chemical significance and characterization of molybdenum disulfide and hexagonal boron nitride, their manufacturing and fabrication and applications and limitations in relation with artificial intelligence and with sustainable development goals, along with their future recommendations and abstract. Have a look on molybdenum disulfide. It is a layered inorganic compound having chemical formula MoS2 that occurs naturally as the mineral molybdenite. It is a silvery black solid with a hexagonal layered crystal structure similar to graphite as it appears in the first picture. Its layers consist of plane of molybdenum atoms sandwiched between two planes of sulfur atoms. In the second picture, the green spheres are the molybdenum atoms that are sandwiched between the two layers of sulfur atoms, having a strong covalent bond, while there is a weak van der Waals forces of attraction between the layers which allow easy interlayer sliding. Bulk MoS2 is diamagnetic, which means that they are having paired electrons and electrically a semiconductor, whereas monolayer molybdenum disulfide has a larger direct band gap, which is nearly equal to 1.8 to 1.9 electron volt. Molybdenum disulfide is a chemically robust, which means that they can withstand many adverse conditions, including they are inert to water and many reagents, and thermally stable up to high temperatures. It begins to oxidize in air above nearly at 350 degrees Celsius. Its combination of semiconducting electronic behavior and extremely low friction coefficient, nearly at 0.15 in ambient air, makes molybdenum disulfide both a high performance solid lubricant and a candidate 2D electronic material. Now we will discuss hexagonal boron nitride. It is a two-dimensional layered material composed of alternating boron and nitrogen atoms arranged in a hexagonal honeycomb lattice, structurally analogous to graphene. Here, the gray spheres are the boron atoms and blue spheres are the nitrogen atoms. They are held together by a strong covalent bond, while each hexagonal honeycomb lattice is combined through van der Waals bonding, which is a weak bonding, while the covalent bonding includes boron and nitrogen bonds, and they are sp2 hybridized. Okay, which allow easy exfoliation into atomically thin sheets. hBN is a wide band gap insulator, nearly at 5.9 to 6.0 electron volt, making it electrically insulating but chemically and thermally stable. Due to its atomically smooth surface, low density of charge traps, high dielectric strength, and chemical inertness, hBN is widely used in materials chemistry as an ideal dielectric substrate and encapsulation layer, particularly in van der Waals heterostructures such as molybdenum disulfide or hexagonal boron nitride, where it preserves and enhances the intrinsic electronic and optical properties of the active 2D material. Now we will discuss the layering of molybdenum disulfide and hexagonal boron nitride over each other. It is a two-dimensional van der Waals heterostructure composed of molybdenum disulfide and hexagonal boron nitride. They are stacked layer by layer without forming traditional covalent bonds between the layers. From a materials chemistry point of view, their system is significant because it combines a semiconducting transition metal dichalcogenide. Chalcogenides are actually the elements of group 16, which includes oxygen, sulfur, selenium, tellurium, polonium. These all are ore forming, and the word chalcose is derived from the Greek language, and they have 6 valence electrons. And hexagonal boron nitride have ultra-wide band gap insulating material, and it allows atomic level control of interfaces and enables tuning of electronic, optical, and excitonic properties without changing chemical composition. Unlike bulk heterojunctions, MoS2 and hBN belongs to a class of materials where interfacial chemistry is governed by non-covalent interactions, making it an ideal platform to study structure property relationships in low-dimensional solids. It bridges solid state chemistry, physical chemistry, and nanochemistry. Here are the coatings. This one is the molybdenum disulfide coating, and it causes high corrosion, while the molybdenum disulfide and hBN coatings causes low corrosion. Now we will discuss the chemical bonding and electronic structures. First of all, there is bonding in molybdenum disulfide. As we have discussed earlier, it is a layered transition metal dichalcogenide, and each layer consists of sulfur molybdenum sulfur sandwich structures. The bonding within the layer is a strong covalent ionic MOS bonds, where molybdenum is in +4 oxidation state and sulfur is in -2 oxidation state. In a crystal field environment, molybdenum is in trigonal prismatic coordination, where its d orbital splitting leads to a semiconducting behavior. Now, in this figure, the A part shows that the trigonal prismatic arrangement, where there is a splitting of the d orbital into T2G and EG sets. The EG set is lower in energy, while the DZ square are having 2 electrons, as we have discussed earlier, that it is a diamagnetic material having a paired electrons. So DZ, which is the orbital of the EG, they are low in energy as compared to the other T2G orbitals, while in octahedral complex, the energy level of the T2G orbitals are lower than that of the EG orbitals, and they are having unpaired electrons, which means that they are paramagnetic in octahedral case. Here in the C part, the S edge shows the sulfur atoms and the blue edge shows the molybdenum atoms, and there is a layering of molybdenum and sulfur atoms. The electronic structure shows that the bulk MoS2 has indirect band gap which is nearly equal to 1.2 electron volt, and but monolayer molybdenum disulfide has the direct band gap nearly equal at 1.8 electron volt, and it has strong excitonic effects due to reduced dielectric screening. And the bonding in hexagonal boron nitride is a 3 to 5 layered compound, just analogous to graphene, as we have discussed earlier, that each layer consists of alternating boron and nitrogen atoms in a hexagonal lattice with strong polar covalent boron nitrogen bonds having partially ionic character due to electronegativity difference. As the electronic structures, they have the wide band gap nearly at 5.9 electron volt and electrically insulating, chemical inert, and thermally stable. And the interlayer bonding in molybdenum disulfide and hexagonal boron nitride is there is no covalent bond between molybdenum disulfide and hexagonal boron nitride layers. They are held together by van der Waals forces, which are weak electrostatic interactions. This results in clean interfaces, minimal charge trapping, and preservation of intrinsic electronic structures. In this figure, it shows the A part shows that there is layer by layer heterostructure. Layers are stacked along Z direction, which are out of plane, and triphenylphosphine PPH3 adsorbed on tungsten diselenium surface. And PPH3, which is triphenylphosphine, is an electron donor. But the second layer, which is tungsten diselenium, it shows it is on top, and the molybdenum disulfide is at the bottom, which is a semiconducting tri TMDs. But the last layer, which is hBN, shows that atomically thin dielectric barrier, and hBN is an uh, insulating spacer. The figure B shows that the experimental verification of stack, there is a sharp interfaces shows that the van der Waals bonding, not covalent bondings, and it shows the clean interfaces, minimal defects, and preserve intrinsic electronic property of each layer. And the figure C here shows that the energy band diagram and charge distribution. The A part shows that the upper band diagram and the conduction band side, the EC here, this EC shows the conduction band edge, and EF shows the Fermi level. The red peak here, the red peak shows it represents that the electron density accumulation. Okay, the electron donated by triphenylphosphine. This triphenylphosphine donates the electrons and move into tungsten diselenium and then tunnel through the hBN. Electron transfer direction from triphenylphosphine to tungsten diselenium, then to hexagonal boron nitride, then it goes from molybdenum disulfide to hexagonal boron nitride. The lower band diagram, which is the valence band, it shows that EV is the valence band edge. Here, this EV is the valence band edge. The colored block represents the band offsets of each layer. hBN wide band gap. Here it is a wide band gap, and MoS2 and tungsten diselenium. This MoS2 and tungsten Selenium has the narrow band gaps. The electron density gradient shows the charge redistribution along z direction. Then we will discuss the chemical significance. There is the absence of dangling bonds, which eliminates the surface states. Interfacial chemistry is dominated by physical adsorption, not chemical reaction, and it enables band engineering without alloying or doping. Now we will discuss the characterization of molybdenum disulfide and hexagonal boron nitride hybrid and coatings. The structural and morphological characteristics of molybdenum disulfide and hexagonal boron nitride hybrids were systematically investigated to confirm the formation of van der Waals heterostructures and to correlate nanoscale features with coating performance. High-resolution transmission electron microscopy, which is HRTEM, was employed as a primary tool to directly visualize layers thickness, their flake morphology, and interfacial stacking between molybdenum disulfide and hexagonal boron nitride. HRTEM analysis of molybdenum disulfide and hexagonal boron nitride hybrid powder. It shows that the images recorded at various magnifications reveal the coexistence of few layers, molybdenum disulfide and hexagonal boron nitride nanosheets within the hybrid system. Molybdenum disulfide appears as predominantly as thin, semi-transparent flakes with lateral dimensions ranging from approximately 100 to 500 nanometer, indicative of successful exfoliation into few layer structures. The sheet-like morphology and contrast variations observed in TEM micrographs are characteristic of layer transition metal dichalcogenides and confirm the preservation of molybdenum disulfide crystallinity after hybridization. The hBN phase is distinctly identified as oval-shaped or pellet-like nanosheets with diameters in the range of 60 to 120 nanometer. This morphology is consistent with exfoliated or mechanically processed hBN, where fragmentation leads to rounded nanosheets rather than extended plate-like structures. The relatively smaller size of hBN compared to molybdenum disulfide facilitates its effective distribution along molybdenum disulfide surfaces, promoting intimate interfacial contact. Then we will discuss the formation of molybdenum disulfide and hexagonal boron nitride heterostructures. A key observation from HRTEM image is the presence of a sandwich-like heterostructures in which a molybdenum disulfide nanosheet is encapsulated between the two hBN layers. This configuration is a hallmark of van der Waals heterostructures formed through weak interlayer interactions without the need of the lattice matching or covalent bonding. The atomically smooth and chemically inert nature of hBN allows it to act as an encapsulation layer, preserving the structural integrity of molybdenum disulfide while minimizing the defect-induced degradation. The formation of such stacked architectures confirms strong interfacial adhesion governed by van der Waals forces and electrostatic interactions. Similar molybdenum disulfide and hexagonal boron nitride stacking arrangements have been widely reported to enhance charge screening and suppress environmental degradation and stabilize the electronic structure of molybdenum disulfide by isolating it from ambient oxygen and moisture. Have a look on the implications for coating microstructures. When incorporated into coatings, the molybdenum disulfide hexagonal hybrid exhibits a brick and mortar-like architecture, where molybdenum disulfide provides a solid lubrication and load-bearing capability, while hBN functions as a chemically inert, impermeable barrier. The nanoscale dispersion observed in TEM suggests that hBN sheets effectively fill interlake voids between MoS2 layers, reducing porosity and limiting diffusion pathways for corrosion species. This layered arrangement significantly improves coating density and continuity. hBN's high thermal stability and oxidation resistance complement MoS2, which is otherwise susceptible to oxidized degradation at elevated temperatures or under tribiological stress. The encapsulation of molybdenum disulfide by hexagonal boron nitride observed in HRTEM directly explains the enhanced antioxidation and anti-corrosion performance of molybdenum disulfide and hexagonal boron nitride hybrid coatings reported in the literature. Then the correlation with functional performance includes the nanoscale heterostructures identified through HRTEM plays a critical role in determining coating performance, the presence of few layer molybdenum disulfide ensures a low shear strength and excellent lubricity, while HBN layers act as a diffusion barrier that blocks oxygen, water, and aggressive ions. Such synergistic effects are responsible for improved wear resistance, reduced friction coefficients, and prolonged coating lifespan under harsh operating conditions. Overall, HRTEM characterization confirms the successful synthesis of a molybdenum disulfide and hexagonal boron nitride van der Waals hybrids, and it validates the formation of sandwich-like heterostructures and provides direct structural evidence linking nanoscale morphology to macroscopic coating performance. Here are some of the characterization of molybdenum disulfide and hexagonal boron nitride hybrid end coatings. In the figure A, it shows that there are the few layers of molybdenum disulfide flakes at 200 nanometer, while the B shows that HBN pellets, but and the C figure shows that molybdenum disulfide flakes at 100 nanometer. Then the D figure shows that HBN aggregates at 50 nanometer. Then the E figure shows that there is a layering of HBN and MoS2, layer by layer arrangement of them, MoS2 and HBN heterostructures. The first layer is HBN layer, the second one is the molybdenum disulfide layer, the last is hexagonal boron nitride layer at 5 nanometer. Here it shows that there is a corrosion protection and solid lubrication, and there is oxygen, water, and corrosive ions. Then we will discuss the manufacturing and fabrication through chemical methods. A variety of techniques are used to prepare molybdenum disulfide based solid lubricant coatings. They include physical vapor deposition, chemical vapor deposition, burnishing, resin bonding, spraying, flame spraying, electrode deposition, and dipping. Majority of the molybdenum disulfide coating employed for tribological applications are prepared using PVD technique, particularly sputtering. However, this technique is expensive and require vacuum to operate. CVD grown 2D molybdenum disulfide are of great interest as solid lubricants for micro nanoscale mechanical systems. Most of the current applications that use molybdenum disulfide as a solid lubricant coating require comparatively thicker tribofilm, limiting the use of CVD grown MoS2. But burnishing and resin bonding are traditional methods used for achieving dry, self lubricating MoS2 films on solid surface. Burnishing, one of the cheapest film deposition techniques, involves the rubbing of the metal surface against molybdenum disulfide powder and subsequent transfer of molybdenum disulfide on the metal surface to form a thin lubricant film. However, this technique lacks adhesion of powder on the substrate since they don't use any binder. On the other hand, in resin bonding, MoS2 solid lubricant film is deposited onto the substrate using a polymer resin as a binder. The coating formulation consists of a solid lubricant material, MoS2, dispersed in a binder matrix, epoxy, or a polymer. The coatings can be applied by spraying, painting, dipping, or spin coating. Depending on the dispersion concentration of molybdenum disulfide, the friction characteristics and corrosion properties tend to change. First of all, we will discuss the mechanical exfoliation, which is a top-down method. In this method, the thin layers of molybdenum disulfide can be obtained by peeling or scotch tape exfoliation of bulk crystals and assembled via dry transfer techniques. This simple method, originally used for graphene, yields a high quality monolayer and few layer flakes, ideal for fundamental studies but is limited in a scale and uniformity, and no chemical reactions are involved. But the second method is the chemical vapor deposition, which is also known as bottom-up method. In this method, first of all, we will discuss the molybdenum disulfide growth and then the HBN growth. In molybdenum disulfide, CVD is widely used to grow large area molybdenum disulfide films on substrates. Common approaches co-evaporate a molybdenum source, for example, molybdenum trioxide or molybdenum metal, with sulfur vapor at high temperature. In typical technique, a small molybdenum trioxide powder board is placed upstream of a heated substrate, with sulfur in a separate board further upstream. The furnace is rammed to nearly at 650 to 800 degrees Celsius. For example, the sulfur at 150 degrees Celsius to sublimate, and the molybdenum trioxide at 600 degrees Celsius, and substrate nearly at 700 degrees Celsius under an argon or argon to hydrogen carrier gas. This converts the molybdenum precursor to molybdenum disulfide on the substrate with optimized conditions. Monolayer or few layer molybdenum disulfide grains or continuous films can be obtained over centimeter scales. Recent reports shows successfully wafer scale monolayer growth by CVD. The process can be tuned temperature, time, and the sulfur to molybdenum trioxide ratio to control layer number, uniform thickness, and grain size. Here is the water in a bubbler, and there is a hydrogen H2S and argon gas which moves from water in a bubbler into the heating belt. Here we will heat all the precursors and molybdenum trioxide and sapphire, and then at 700 degrees Celsius, and then we will get the molybdenum disulfide. The precursors include MOO3, which is molybdenum trioxide, and sulfur vapors, and the chemical reaction includes molybdenum trioxide plus 3 sulfurs gives us molybdenum disulfide plus sulfur dioxide. The growth of molybdenum disulfide on pre-grown hBN substrates yields vertical heterostructures, and the temperature in which this reaction proceeds are 650 to 800 degrees Celsius. In this figure, there is a fast reduction rate. There is hydrogen sulfide, and molybdenum trioxide. These all three are the reactants, and which gives us molybdenum dioxide, and molybdenum dioxide then proceeds with H2S and gives us molybdenum disulfide. But the low reduction rate, it volatile intermediate molybdenum dioxide into two molecules of hydroxide. Here the water molecules when react with molybdenum trioxide, it gives us this product. Then we will discuss the hBN growth. The hBN growth includes the precursors borazine or ammonium borate, and it produces high quality crystalline insulating layers. The chemistry advantages include controlled stoichiometry, tunable thickness, potential for industrial scale synthesis. The third method includes the encapsulation strategy. In this strategy, hBN layers placed above and below MoS2, and it acts as a chemical passivation layer and dielectric barrier, and it prevents oxidation and adsorbate interactions. This mimics solid state solvation where hBN acts as a chemically inert environment. The fourth method is the hydrothermal or solvo thermal synthesis. High temperature liquid phase reactions, autoclave methods can produce MoS2 nanomaterials. Typical precursors include ammonium molybdate or molybdenum trioxide with sulfur source such as thiourea or hydrogen sulfide. Reacted at nearly 180 to 220 degrees Celsius in water, these precursors grow molybdenum disulfide in situ, often yielding nanosheets or nanoflowers. For example, dissolving ammonium heptamolybdate and thiourea in water and heating in a Teflon autoclave yield layered molybdenum disulfide, often the 1T phase. Hydrothermal methods are relatively simple and can produce bulk quantities of nanostructured MoS2 for catalysts, batteries, etc. Through layer thickness and crystallinity are harder to control precisely. First of all, we will stir the molybdenum, ammonium molybdate and thiourea for 60 minutes. Then it goes into the autoclave, which is made up of the Teflon layered autoclave. Then there is a centrifugation at 4000 RPM. Then there is a filtration process, and we will dry the filtrate at 60 degrees Celsius, and then we will get the molybdenum disulfide nanostructures. One of the necessary conditions for obtaining ultra low friction of molybdenum disulfide is the absence of contaminants such as humid air or oxygen. Molybdenum disulfide swiftly oxidizes to molybdenum trioxide in an oxygen or moist air environment, and this oxidation rate significantly increases with relative humidity. The presence of molybdenum trioxide promotes the chemisorption of water and thermally shows a higher COF. In addition, molybdenum disulfide enhances corrosion by stimulating the oxygen reduction reaction. Moreover, it can form corrosion microcells with the surrounding metal when added as a filter to metal matrices, resulting in a lower corrosion resistance than pure metal. Even though MoS2 is highly lubricating, uh, MoS2 is highly lubricating. The corrosive nature of this dry solid lubricant limits its application in oxidizing and humid environment. There is currently no lubricant alternative in the industry to bring COF as low as molybdenum disulfide. So extending the range of working environments for molybdenum disulfide is a significant technical challenge for corrosion engineers. Fewer efforts have been made to improve the corrosion characteristics of molybdenum disulfide nanosheets coatings, and they are prepared molybdenum disulfide zirconium composite coatings by closed field unbalanced magnetron sputtering to study their tribological properties in a highly humidity environment. The zirconium inclusion resulted in a low COF at 68% relative humidity compared to pure molybdenum disulfide film doped molybdenum disulfide nanosheets with transition metals such as iron, cobalt, and nickel, aiming to improve the corrosion resistance of molybdenum disulfide, a composite of hydrogenated amorphous carbon and molybdenum disulfide film fabricated by using reactive magnetron sputtering technique aimed to expand the application of molybdenum disulfide anti-friction and corrosion resistance coating. The composite film exhibited excellent corrosion and water resistance compared to the pure molybdenum disulfide coating, successfully achieving excellent corrosion and anti-friction properties for titanium doped molybdenum disulfide coating. By introducing hydrogen-free carbon chromium coating fabricated using layer-by-layer deposition technique, the enhancement in corrosion resistance was ascribed to the heterogeneous interfaces in multi-layer coating that inhibited the permeation of corrosive medium. Several recent works have been reported using molybdenum disulfide and other materials, RGO, CNF, selenium dioxide, PDA, etc., as filler materials for epoxy coatings, resulting in excellent corrosion resistance. The increased dispersibility of molybdenum disulfide and other materials in the epoxy material matrix through surface modification and the barrier effect of filler materials resulted in the enhancement of corrosion resistance. The hexagonal boron nitride is a 2D material with layered heterostructures. Because of its chemical inertness and impermeability, HBN is an excellent candidate for anti-corrosion and high-temperature oxidation-resistant coatings. Moreover, the anti-friction properties of HBN have also been explored. However, the brittle nature, low fracture strength upon impact of HBN limit its application in solid lubrication. Coatings of van der Waals heterostructures of molybdenum disulfide and hexagonal boron nitride nanosheets have been shown to improve the corrosion properties of molybdenum disulfide. In electronic applications, HBN is used as an encapsulation for molybdenum disulfide to protect it from contamination and degradation. Prepared 2D heterostructure coatings of molybdenum disulfide and hexagonal boron nitride and incorporation of HBN into molybdenum disulfide layers increased the corrosion resistance of heterostructure coating compared to pure molybdenum disulfide coating. The improvement in corrosion resistance was attributed to the insulating property of HBN. However, the tribological properties of the heterostructure coating were not reported. The incorporation of modified materials in higher concentration into the matrix may lead to drastic changes in the anti-friction properties of the coating. As of now, there are no studies reported on both wear and corrosion resistance properties of molybdenum disulfide and hexagonal boron nitride coatings. The present work aims to develop a hybrid coatings of molybdenum disulfide and hexagonal boron nitride nanosheets with the varying hexagonal boron nitride concentrations and study the effect of hexagonal boron nitride concentration on the corrosion and anti-friction properties of the coating. Now there is the importance of molybdenum disulfide and hexagonal boron nitride in chemistry, the model system for studying the non-covalent interactions in solids and excitons and charge screening, interface controlled reactivity. Now we will discuss the applications of molybdenum disulfide and hexagonal boron nitride. The first of it includes the protective and anti-corrosion coatings. As we have discussed earlier, the molybdenum disulfide and hexagonal boron nitride structures, heterostructures, are widely used in protective coatings due to their complementary chemical and physical properties. In implementation, exfoliated MoS2 nanosheets are mixed with HBN platelets and incorporated into polymeric or metallic matrices through techniques such as electrophoretic deposition, spraying coating, and sol-gel processing. Chemically, molybdenum disulfide provides a layer solid lubricant phase with low shear strength, while HBN acts as an inert diffusion barrier that blocks oxygen, um, moisture, and aggressive ions. The resulting brick and mortar microstructure significantly reduces corrosion pathways and suppresses molybdenum disulfide oxidation, thereby improving coating durability in marine, aerospace, and industrial environments. In this picture, there is the first coating is the molybdenum disulfide coating, and there is the high corrosion. When there is layer by layer coating of molybdenum disulfide and hexagonal boron nitride, these two coatings act as uh, and these two coatings causes the low corrosion, and they act as a protective or anti-corrosion coatings. The second is the solid lubrication and tribiological engineering. In tribiological engineering applications, molybdenum disulfide and hexagonal boron nitride hybrids are implemented as dry lubricants or lubricant additives. In mechanical systems, MOS2 nanosheets slide easy due to weak interlayer van der Waals forces, providing ultra-low friction, while HBN stabilizes the lubricating film under high temperature and oxidative conditions. From a materials science perspective, the hybrid is applied by embedding the nanosheets into surface coatings or greases, whereas the HBN enhances the thermal stability and wear resistance. This combination is extensively used in vacuum systems, aerospace bearings, MEMs, NEMS devices, and high load mechanical contacts where conventional liquid lubricants fails. The third application is the energy storage and conversion systems. Molybdenum disulfide and hexagonal boron nitride heterostructures are implemented in electrochemical devices such as lithium-ion batteries, sodium-ion batteries, and supercapacitors. Chemically, molybdenum disulfide acts as the active electrode material facilitating ion intercalation, while the hexagonal boron nitride serves as a structural stabilizer and dielectric spacer that prevents molybdenum disulfide restacking. In practical implementation, the hybrid material is synthesized via hydrothermal and chemical vapor deposition methods and coated onto current collectors. This architecture enhances the cycling stability, charge transport, and electrochemical durability, making molybdenum disulfide and hexagonal boron nitride promising for next generation energy storage and hydrogen evolution catalysis. The fourth application is in nanoelectronics and optoelectronic devices. In electronic engineering, molybdenum disulfide and hexagonal boron nitride heterostructures are implemented as van der Waals stacks into the electronic devices. Molybdenum disulfide functions as a semiconducting channel with a tunable bandgap, while hexagonal boron nitride is used as an atomically smooth dielectric substrate and encapsulation layer. Device fabrication involves layer by layer transfer or CVD, chemical vapor deposition growth. The presence of hexagonal boron nitride minimizes charge trapping and surface roughness, leading to enhanced carrier mobility and device stability. The heterostructures are applied in field effect transistors, photodetectors, flexible electronics, and optoelectronic sensors. There is a picture which shows the protective layer coating. There is a selenium dioxide and then hexagonal boron nitride, and there is a protective layer. The figure B shows that there are the 11 layers of hexagonal boron nitride, and these are shown at 0.33 nanometer or 0.38 nanometer, while the C shows that there is a graph between the brightness and the distance, and there are the peaks at 0.38 and 0.33. And the figure shows that they're at different points. The resolution of this figure shows that the layering at different points. And there are the graphs between energy loss and intensity, and it shows the different peaks. The fifth application is in artificial intelligence and machine learning driven engineering. AI and machine learning are increasingly used to optimize the design and development of molybdenum Deployment of molybdenum disulfide and hexagonal boron nitride systems. Machine learning algorithms are trained on experimental and stimulation data sets to predict optimal layer thickness and composition ratio, friction coefficient, and corrosion resistance. In implementation. AI accelerators materials discovery by integrating density functional theory (DFT) calculations with predictive models, significantly reducing trial and error experimentation. In engineering systems, AI-enabled sensor combined with molybdenum disulfide and hexagonal boron nitride coatings enable real-time monitoring of wear, friction, and degradation, supporting predictive maintenance and smart manufacturing. The sixth application includes smart sensors and environmental monitoring. Molybdenum disulfide and hexagonal boron nitride hybrids are implemented in chemical and gas sensors due to molybdenum disulfide's high surface sensitivity and hBN stabilizing role in sensor fabrication. Molybdenum disulfide and hexagonal boron nitride films are deposited on electrodes where adsorption of target molecules alters electrical and optical signals. HBN protects the sensing layer from environmental degradation, improving reproducibility and lifetime. These sensors are used in environmental monitoring, industrial safety, and air quality detection, offering high sensitivity, selectivity, and long-term operational stability. The seventh application is in biomedical and medical applications. In biomedical engineering, molybdenum disulfide and hexagonal boron nitride heterostructures are implemented in drug delivery systems, biosensors, and biointerfaces. Molybdenum disulfide provides a large surface area for drug loading and photothermal activity, while HBN enhances biocompatibility and chemical stability. Chemically functionalized molybdenum disulfide and hexagonal boron nitride nanosheets are used to transport therapeutic agents and release them in a controlled manner under specific stimuli. Additionally, molybdenum disulfide and hexagonal boron nitride based biosensors are employed for detecting biomarkers, DNA, and proteins with high sensitivity, enabling applications in diagnostics and personalized medicines. The eighth application is in water purification and environmental remediation. Molybdenum disulfide and hexagonal boron nitride hybrids are implemented in membrane-based filtration and adsorption systems for water treatment. Layered molybdenum disulfide and hexagonal boron nitride membranes are fabricated through vacuum filtration or layer by layer assembly, enabling selective ion transport and molecular sieving. Molybdenum disulfide provides adsorption sites for heavy metals, while hexagonal boron nitride improves mechanical strength and chemical resistance. These systems are applied in desalination, wastewater treatment, and pollutant removal, contributing to sustainable environment technologies. The ninth application is in nano and microelectronics. High performance field effect transistors, which are also known as FETs. In nano and microelectronics, molybdenum disulfide and hexagonal boron nitride heterostructures have emerged as a benchmark platform for high performance field effect transistors. In these devices, molybdenum disulfide functions as a semiconducting channel, while hexagonal boron nitride serves as an atomically flat dielectric substrate and encapsulation layer. Unlike conventional selenium dioxide substrates, hexagonal boron nitride exhibits an absence of dangling bonds, low charge trap density, and high dielectric breakdown strength, which significantly suppresses carrier scattering at the interface. This results in enhanced carrier mobility, reduced hysteresis, and improved threshold voltage stability. The chemically inert nature of HBN also protects molybdenum disulfide from environmental degradation and ensuring long-term operational stability and making molybdenum disulfide and hexagonal boron nitride FETs highly attractive for next generation low power and high speed electronic devices. This is a figure, and the left side A shows that the schematic dependence of the hysteresis width versus here is the sweep frequency and hysteresis width in molybdenum disulfide FETs. And the right, this shows that the schematic plot showing that the bias dependence of the distributed capture and emission times EC And the figure B shows that at low frequency, some of the traps which are charged at the initial equilibrium have enough time to emit a whole if their energy level moves from if the energy moves that there is a sweep and if their energy moves Eg at Vg is equals to Vg plus during the V plus sweep. Here is a charge transfer that how the energy transfers from one to another, and there is a hysteresis width that when we increase that current that there is a decrease in the gate voltage. The 10th application is in optoelectronics and photodetectors and light emitting devices. In optoelectronic applications, molybdenum disulfide hexagonal boron nitride heterostructures enable efficient photodetectors, light emitting devices, and excitonic systems. Monolayer and few layer molybdenum disulfide possesses a direct bandgap and strong light matter interactions. However, their optical performance is often limited by non-radiative combination caused by substrate defects, and hBN encapsulation significantly enhances photoluminescence efficiency by providing a clean and uniform dielectric environment and minimizes charge impurities and surface roughness. Moreover, hBN improves exciton confinement and stability with molybdenum disulfide, enabling sharper optical transitions and improved quantum efficiency. These properties make molybdenum disulfide and hexagonal boron nitride heterostructures promising for ultra-sensitive photodetectors and flexible optoelectronics and next-generation light-emitting devices. The 11th application is energy conversion and catalysis, which is hydrogen evolution reaction HER. From an energy and catalysis perspective, molybdenum disulfide hexagonal boron nitride heterostructures are actively explored for hydrogen evolution reaction applications. Molybdenum disulfide serves as a catalytically active component with H sites acting as efficient centers for hydrogen absorption and evolution. However, pristine molybdenum disulfide often suffers from limited stability and aggregation under electrochemical conditions. Incorporation of hexagonal boron nitride provides structural support, chemical inertness, and improved dispersion of molybdenum disulfide and layers. Hexagonal boron nitride also enhances durability by preventing oxidation and maintaining the exposure of active sites during long-term operation. The synergistic interaction between molybdenum disulfide and hexagonal boron nitride thus improves catalytic efficiency, operational stability, and sustainability, positioning these heterostructures as a viable alternatives to noble metal-based catalyst. These are different MoS2 for her. This is the delta G in which the T1 phase and N2H phase, and there are the defects which are intrinsic and then doped, which are the active sites, and then it goes into the morphology, which is the vertical position. There is a vertical arrangement, and these are the heterophilicity. And the fourth one is the conductivity. Conductivity includes the interfacial conductivity of the interfacial heterostructures, and there is a explanation of this pie chart. The 12th application is in quantum technology and AI related applications. In emerging quantum and AI-related technologies, molybdenum disulfide and hexagonal boron nitride heterostructures are investigated for low-power electronics, neuromorphic computing, and ultra-sensitive sensing platforms. The atomically clean interfaces provided by hBN significantly reduces defect density and electronic noises, which is critical for quantum transport and signal fidelity. Molybdenum disulfide and hexagonal boron nitride stacks enables precise control of charge carriers, excitonic states, and tunneling phenomena, which are essential for neuromorphic architectures that mimic biological neural networks. Additionally, these heterostructures are compatible with AI-driven device optimization, where machine learning algorithms are used to tune layer thickness, stacking order, and device geometry to achieve optimal performance in sensing and computing applications. The 13th application is the flexible and wearable sust- and sustainable electronics. The exceptional mechanical flexibility and thermal stability of molybdenum disulfide and hexagonal boron nitride heterostructures make them highly suitable for flexible electronics and wearable sensors technologies. Both materials retain their electrical and structural properties under bending, stretching, and thermal cycling, allowing integration into lightweight and deformable substrates. In wearable devices, molybdenum disulfide and hexagonal boron nitride based sensors offer high sensitivity, environmental stability, and low power consumption. From a sustainability perspective, these heterostructures support green and energy efficient material design due to their reduced material usage, long service life, and compatibility with low temperature fabrication processes. Consequently, molybdenum disulfide and hexagonal boron nitride systems align well with the principles of sustainable electronics and next generation eco-friendly. 14th and the last application includes the future technologies and emerging fields. Emerging applications of molybdenum disulfide and hexagonal boron nitride include quantum devices, neuromorphic computing, and space technologies. In these implementations, precise control, overstacking order, and twist angle enables tunable electronic and optical properties. hBN protects molybdenum disulfide from radiation damage and extreme environments, making the heterostructure suitable for space electronics and advanced computing architectures. Integrating with AI controlled fabrication techniques further enhances scalability and performance. It spans several advanced areas of material chemistry, electronics, and sustainable technology due to their chemically clean interface, excellent dielectric properties, and tunable electronic behavior. In nano and microelectronics, molybdenum disulfide is widely used in high performance field effect transistors, as we have discussed earlier, where HBN acts as atomically flat dielectric substrate and encapsulation layer, significantly improving carrier mobility and device stability compared to conventional silicon dioxide based systems. In optoelectronics, the heterostructure enables photodetectors, light emitting devices, and excitonic devices as enhances photoluminescence efficiency and exciton confinement in molybdenum disulfide. From an energy and catalysis perspective, molybdenum disulfide and hexagonal boron nitride systems are explored for hydrogen evolution reaction, as we have discussed earlier, where molybdenum disulfide serves as a catalytic active layer and hBN provides chemical stability and support. In quantum and AI related technologies, molybdenum disulfide and hexagonal boron nitride heterostructures are investigated for low power electronics, neuromorphic computing, and ultra sensitive sensors, benefiting from reduced noise and defect density. Additionally, their mechanical flexibility and thermal stability make them suitable for flexible electronics, wearable sensors, and next generation sustainable devices, aligning well with green and energy efficient material design principles. Now we will discuss the limitations of molybdenum disulfide and hexagonal boron nitride heterostructures. The first limitation is the large scale synthesis and scalability challenges. One of the major limitations of molybdenum disulfide and hexagonal boron nitride heterostructures is the difficulty in achieving large-scale uniform and reproducible synthesis. While mechanical exfoliation and layer-by-layer transfer yield high-quality heterostructures, these methods are not industrially scalable. Chemical vapor deposition, through although promising, often leads to non-uniform layer thickness, grain boundaries, and uncontrolled stacking orientation. Such variability directly affects electronic, optical, and catalytic performance, limiting commercial implementation. The second one is the interfacial defects and contamination. Despite the van der Waals nature of molybdenum disulfide and hexagonal boron nitride interfaces, trapped contaminants such as hydrocarbons, moisture, or polymer residues during fabrication can introduce interfacial defects. These trapped species create charge inhomogeneities, reduce carrier mobility, and degrade optical properties. In electronic and optoelectronic devices, even minimal interfacial contamination can significantly impact device performance and reliability, especially at nanoscale dimensions. The third one is the weak interlayer coupling. It includes the absence of covalent bonding between MoS2 and hBN results in weak interlayer coupling, which is the van der Waals forces, as we have discussed earlier, while beneficial for preserving intrinsic properties, limits charge transfer across interface. This weak coupling can restrict applications that require strong electronic and catalytic interactions between layers, such as high efficiency photocatalysis or vertical electronic transport devices. The fourth limitation is limited thermal and environmental stability of molybdenum disulfide. Although hexagonal boron nitride provides partial encapsulation and protection, molybdenum disulfide itself remains susceptible to, to oxidation and degradation at elevated temperatures or under prolonged exposure to harsh chemical environments. Incomplete or non-uniform hBN coverage can expose molybdenum disulfide edges and defects leading to performance degradation over time. This limitation is particularly critical in high-temperature electronics and catalytic applications. The fifth limitation is the band alignment and device design constraints. The fixed wide band gap of hexagonal boron nitride nearly at 6 electron volt imposes constraints on band alignment engineering in molybdenum disulfide and hexagonal boron nitride structures. While hexagonal boron nitride is excellent as a dielectric, it limits tunability for applications requiring active electronic participation from both layers. Achieving optimal band alignment for advanced optoelectronic and tunneling devices often requires additional layers or complex heterostructure engineering. The sixth one is the high fabrication cost and complexity. The fabrication of high quality molybdenum disulfide and hexagonal boron nitride heterostructures typically involve sophisticated equipment, clean room facilities, and multi-step processing including exfoliation, transfer, alignment, and encapsulation. Processing these processes increase production costs and reduce throughput, making large-scale commercialization economically challenging compared to conventional materials. The seventh one is the mechanical integration issues. While individual molybdenum disulfide and hexagonal boron nitride exhibits excellent mechanical flexibility, their integration into multilayer heterostructures can lead to delamination or interlayer slippage under mechanical stress. This issue becomes significant in flexible and wearable electronics, where repeated bending or stretching can degrade interfacial integrity and device performance. The eighth one is a limited understanding of long term reliability. Despite extensive laboratory studies, the long term reliability and aging behavior of molybdenum disulfide and hexagonal boron nitride heterostructures under real world operating conditions remain insufficiently understood. Factors such as thermal cycling, humidity exposure, radiation, and mechanical fatigue can introduce degradation mechanisms that are not fully captured in short term experimental studies. It arises both materials chemistry and technological perspectives. One major challenge is the complex and energy intensive synthesis, as high quality hBN and MoS2 often require high temperatures and controlled environments, making large scale, cost effective fabrication difficult. Achieving uniform defect free, large area heterostructures remain challenging, particularly in CVD growth films, where grain boundaries, thickness variations, and interfacial contaminations can degrade electronic and optical performance. From a structural standpoint, precise control over stacking order and twist angle is difficult, yet these parameters strongly influence excitonic behavior and Moir effects. Additionally, although HBN provides an excellent dielectric interface, it is electrically insulating, which can limit charge injection and increase contact resistance in device architectures. Environmental and sustainability concerns also exist, include limited recyclability of 2D materials, lack of long-term stability data, stability data under real operating conditions, and high production costs of high purity HBN. Collectively, these limitations highlight the need for improved synthesis strategies and scalable manufacturing and sustainable processing routes before widespread industrial adoption of molybdenum disulfide and hexagonal boron nitride heterostructures can be achieved. Then we will discuss the relation of molybdenum disulfide and hexagonal boron nitride with artificial intelligence AI. The relation between molybdenum disulfide and hexagonal boron nitride heterostructures and artificial intelligence is twofold. AI as a tool to design and optimize molybdenum disulfide and hexagonal boron nitride materials, and molybdenum disulfide and hexagonal boron nitride as a material platform enabling AI hardware and intelligent systems. This synergy bridges materials chemistry, device physics, and data-driven engineering. The first is AI-assisted design and optimization of molybdenum disulfide and hexagonal boron nitride materials. Artificial intelligence, particularly machine learning, plays a crucial role in accelerating the discovery and optimization of molybdenum disulfide and hexagonal boron nitride heterostructures. By training machine learning models uh, on experimental data and first principles stimulations, DEF, AI can predict optimal layer thickness, stacking order, twist angle, and composition ratio that maximizes desired properties such as carrier mobility, friction reduction, or catalytic activity. This data driven approach reduces the reliance on trial and error experiments and enables rational materials design, significantly shortening development cycles in materials chemistry and nanotechnology. The second one is a neuromorphic computing and brain inspired devices. In neuromorphic systems, molybdenum disulfide and hexagonal boron nitride heterostructures are used to fabricate artificial synapses and memristive devices. The atomically sharp interfaces allow precise modulation of charge transport, enabling synaptic behaviors such as learning, memory retention, and plasticity. AI algorithms are employed to tune device parameters and optimize learning rules, while the material itself supports energy efficient signal processing. This integration represents a critical step toward hardware based AI that overcomes the energy limitations of conventional silicon based computing. Here is the figure. A shows that the systematic illustration of biological synapse in a neuron system and our synaptic stack channel fed for neuromorphic function. There is the presynaptic neuron and there is a synapses. Neurotransmitters are given and the receptors receive. Then there is a postsynaptic neuron. And the figure B shows that the transfer curves of molybdenum diselenium or molybdenum disulfide stack channel memory FET showing asymmetric memory hysteresis behavior as measured under the double sweep of VGS, and the OM image of a molybdenum diselenium or molybdenum disulfide stack channel memory FET. And the figure D shows that the 2D systematic structures of our molybdenum diselenium or molybdenum disulfide stack channel FET to describe electron traps as a molybdenum diselenium or molybdenum disulfide heterojunction interface. And the figure E shows that the band diagram of molybdenum diselenium or molybdenum disulfide heterojunction and analytical energy band diagrams of channel FET under corresponding D. The third relation shows that the molybdenum disulfide and hexagonal boron nitride as an enabling platform for AI hardware. Molybdenum disulfide and hexagonal boron nitride heterostructures are increasingly explored as building blocks for next generation AI hardware. Molybdenum disulfide serves as a semiconducting channel with excellent electrostatic control at a nanoscale, while HBN provides an ultra clean dielectric environment with minimal charge trapping. This combination allows low power, high stability transistors essential for neuromorphic computing and edge AI devices. The reduced noise and defect density offered by HBN encapsulation molybdenum disulfide are particularly advantageous for analog computing architectures that mimic biological neural networks. The fourth one is the AI enhanced sensors based on molybdenum disulfide and hexagonal boron nitride. Molybdenum disulfide and hexagonal boron nitride based sensors generate large and complex data based datasets due to their high sensitivity to chemical, biological, and physical stimuli. AI and machine learning techniques are applied to process these datasets, enabling pattern recognition, noise reduction, and real time decision making. In practical implementations, molybdenum disulfide provides high surface reactivity for sensing, while hexagonal boron nitride ensures signal stability and environmental protection. AI algorithms further enhances selectivity and accuracy, making these sensors suitable for smart healthcare, environmental monitoring, and industrial automation. The fifth one is the predictive maintenance and smart engineering systems. It includes molybdenum disulfide and hexagonal boron nitride heterostructures are employed in smart coatings and tribological systems where AI is used to analyze friction, wear, and degradation data in real time. Machine learning models trained on sensor data can predict failure modes, optimize lubrication conditions, and extend component lifetimes. In this context, molybdenum disulfide and hexagonal boron nitride materials enable reliable sensing and protection, while AI provides intelligence and autonomy to engineering systems. The sixth one is the AI guided manufacturing and process control. AI also supports the scalable manufacturing of molybdenum disulfide and hexagonal boron nitride heterostructures by optimizing synthesis parameters such as temperature, pressure, precursor concentration, and deposition time. Machine learning models analyze process data to ensure uniformity, defect minimization, and reproducibility. This integration of AI with materials processing is essential for translating molybdenum disulfide and hexagonal boron nitride technologies from laboratory scale demonstration to industrial applications. The seventh one is the AI sustainability and smart materials. From a sustainability perspective, AI-assisted optimization of molybdenum disulfide and hexagonal boron nitride heterostructures contributes to green and energy-efficient technologies. AI minimizes the materials waste, reduces energy consumption during fabrication, and enables longer lasting devices. When deployed in AI enabled electronics, sensors, and energy systems, molybdenum disulfide and hexagonal boron nitride heterostructures support intelligent and sustainable technological ecosystems. Molybdenum disulfide and hexagonal boron nitride heterostructures play a crucial role in the development of next generation AI hardware, particularly where low power consumption, high speed, and miniaturization are required. In AI systems, data processing increasingly relies on energy efficient transistors, sensors, and neuromorphic devices, and molybdenum disulfide hexagonal boron nitride provides a material solution to these challenges. Molybdenum disulfide acts as a semiconducting channel with a tunable bandgap, while hBN serves as ultra clean dielectric encapsulation layer, significantly reducing charge traps and electronic noise. This results in higher carrier mobility, low leakage current, and stable operation, which are essential for AI accelerators and edge AI devices. The fourth one is the strong excitonic and optoelectronic properties of molybdenum disulfide and hexagonal boron nitride enable AI-enabled photonic sensors used in image recognition and environmental monitoring and biomedical diagnostics. From a materials discovery perspective, AI and machine learning algorithms are also used to optimize MOS2 hBN synthesis, predict defect behavior, and design heterostructures with tailored electronic properties, accelerating materials development. Now, the second last is the relation of molybdenum disulfide and hexagonal boron nitride heterostructures with sustainable development goals. Molybdenum disulfide and hexagonal boron nitride heterostructures contribute to multiple sustainable development goals by enabling advanced materials that are energy efficient, durable, and environmentally responsible. Their unique combination of high performance and long operational lifetime supports sustainable industrial development, clean energy technologies, and improved quality of life. First of all is the SDG 7, which is affordable and clean energy. MOS2 and hexagonal boron nitride heterostructures play important role in clean energy generation and storage technologies. In hydrogen evolution reaction, her systems, MOS2 serves as an efficient earth-abundant catalytic material while hBN enhances chemical stability and durability under electrochemical conditions. This combination reduces reliance on expensive noble metal catalysts and improves catalyst lifetime, making green hydrogen production more affordable and scalable. Additionally, their application is energy efficient. Electronics and batteries contribute to reduced energy consumption and improved energy utilization. Second relation is with SDG 9, which is industry, innovation, and infrastructure. The development of MOS2 and HBN based electronics, coatings, and sensors supports sustainable industrial innovation. High performance MOS2 and HBN field effect transistors enable low power electronic devices, while protective and anti corrosion coatings extend the lifetime of industrial components and infrastructure. By reducing maintenance requirements and material degradation, these heterostructures help build resilient and resource efficient industrial systems aligned with sustainable infrastructure development. Now, the third is their relation with SDG 12, which is responsible consumption and production. MOS2 heterostructures promote responsible production through materials efficiency and durability. Their atomically thin nature enables high performance with minimal material usage, reducing raw material consumption. Furthermore, AI assisted synthesis and optimization of molybdenum disulfide and hexagonal boron nitride systems minimize waste, energy use, and trial and error experimentation. The longer service life of molybdenum disulfide and hexagonal boron nitride based devices and coatings also reduces the frequency of replacement, supporting sustainable manufacturing practices. Then their relation is with the SDG 9, which is good health and well being. In healthcare and biomedical applications, molybdenum disulfide and hexagonal boron nitride heterostructures contribute to improved diagnostics and medical technologies. Their use is in biosensors, enable early disease detection through highly sensitive and stable sensing platforms. Additionally, molybdenum disulfide and hexagonal boron nitride based antimicrobial and anti-fouling surfaces can reduce hospital acquired infections, enhancing patient safety. This chemical stability and biocompatibility of HBN further support safe biomedical device integration. Now, there is a relation with SDG 6, which is clean water and sanitation. Molybdenum disulfide and hexagonal boron nitride heterostructures are increasingly explored for water purification and environmental remediation. Layered molybdenum disulfide and hexagonal boron nitride membranes exhibit selective ion transport and high chemical resistance, making them suitable for desalination, heavy metal removal, and wastewater treatment. These techniques contribute to improved access to clean water and suitable water management, particularly in resource limited regions. Now, there is a relation with SDG 9, which is sustainable cities and communities. Their applications of molybdenum disulfide and hexagonal boron nitride in smart sensors, flexible electronics, and environmental monitoring supports the development of sustainable and resilient cities. Molybdenum disulfide and hexagonal boron nitride based sensors can be integrated into infrastructure for real time monitoring of air quality, structural health, and energy usage. Their low power operation and durability make them ideal for long term deployment in urban environments. Now, the last relation is with SDG 13, which is climate action. By enabling energy efficient devices, green hydrogen production, and long lasting materials, MOS2 and HBN heterostructures contribute indirectly to climate change mitigation, reduced energy loss in electronics, extended component lifetimes, and improved renewable energy technologies help lower greenhouse gas emissions and carbon footprints across industrial and technological sectors. Molybdenum disulfide and hexagonal boron nitride heterostructures align with multiple United States Sustainable Development Goals by enabling energy efficient and sustainable and high performance technologies. Then there is a relation with SDG 9, which is low power electronics support SDG 9 by reducing energy consumption in computing and communication systems. And in clean energy applications, MOS2 is efficient catalyst for hydrogen evolution reaction, while HBN provides chemical stability contributing to SDG 13 climate action through green hydrogen production. The development of advanced nanoelectronics and AI compatible devices uses Molybdenum disulfide and hexagonal boron nitride supports SDG 9 industry innovation and infrastructure by promoting sustainable industrial innovation. Their application in smart sensors and environmental monitoring systems contributes to SDG 11, which is sustainable cities and communities, enabling intelligent infrastructure with lower energy demands. Furthermore, the atom thin nature of these materials promote resource efficiency and reduced material usage, aligning with SDG 12, which is responsible consumption and production. And now have a look on the abstract of this topic, which is molybdenum disulfide is commonly utilized as a solid lubricant due to its outstanding wear resistance properties. However, the application of molybdenum disulfide is restricted due to its high tendency of oxidation and corrosion when exposed to oxygen and humid air. Hence, in this work, we developed a 2D hybrid structure by incorporating a 2D material, the hexagonal boron nitride, with molybdenum disulfide to enhance the corrosion resistance properties. Molybdenum disulfide and hexagonal boron nitride 2D hybrid coatings with varying concentration of hexagonal boron nitride nanosheets were deposited onto mild steel specimens to evaluate tribological and corrosion properties. The friction studies were carried out using a high frequency reciprocating tribometer and found that hybrid coatings showed a slightly higher coefficient of friction um, than pure molybdenum disulfide coating due to hBN addiction. Electrochemical corrosion studies of the coating were conducted in 3.5% weightage of NaCl solution, potentiodynamic polarization, and electrochemical impedance spectroscopy studies depicted lower corrosion rate and higher corrosion resistance for molybdenum disulfide and hexagonal boron nitride coatings than pure molybdenum disulfide coatings. The increase in hexagonal boron nitride content resulted in an enhanced corrosion resistance. Raman spectroscopy study of corroded coatings revealed the presence of the high concentration of molybdenum trioxide in pure molybdenum disulfide coating, while oxide peaks were nearly absent in molybdenum disulfide and hexagonal boron nitride coatings. XPS analysis depicted comparatively low oxidation of molybdenum trioxide concentration in hybrid coatings compared to pure molybdenum disulfide coatings. Then these all are the references from which I have collected my material. I hope you understand this. If you have any query, you can ask in the comment section. Okay, thank you.